We are going to take this equation, this first law equation, and we are going to have to read what the problem statement is telling us with our secret decoder ring and find out what is it trying to say. How are we going to use this equation for the problems? And so the first thing that we're going to assume right away for almost every problem is going to be steady state. If we have steady state, what this means is the properties are not changing with time. Okay? Well, the properties of energy are not changing with time. And so this is going to mean that the change in energy of our control volume with respect to time is equal to 0. So whenever you see the word steady state, or you're going to assume that we are running a problem at steady state, that means that the change of energy with respect to time is equal to 0. Now let's be honest. If we look at this, because we've been honest the whole lecture, right? We've been honest and open this whole lecture. Steady state, we start with a transient period, and then we have a steady state period. And steady state kind of isn't quite like a barn, straight on. It's approximately steady state. So here we're approximating the steady state. This, of course, we know this is our transient period. But this is why we model it as steady state. Okay, and I give that old analogy. We're now on the interstate, and we have our cruise control at 75 miles an hour. It doesn't mean that the whole time we're going to go 75 miles an hour. We may be going up hills and down hills, and our speed is going to change just a little bit. But we're modeling it at 75 miles an hour. How fast did you get here? They say, what were you going on the speed limit on the interstate? I was going 75. You don't say, I was going 75, and sometimes I was going 72, and other times I was going 86. I was going 86. That's probably off the bounds of steady state. 86, 78 is what I was trying to say. 78. You can go up and down a little bit there, but it's pretty much that you're going 75 miles an hour. So steady state is the model we're going to have for almost every one of our problems now. It's going to state it explicitly many times, but other times it's not going to state it explicitly, and we're going to have to assume it's steady state. Now we do deal with transient problems, but that is not until that's not for a while. It's not until the end of next week that we deal with them. And it's very definitive when we will be talking about transient problems in this class. So steady state, that's the first thing we're looking at. Now, sometimes we also have that the heat transfer rate of the control volume is equal to 0. We can eliminate that. Okay, and what do we do there? Well, we have words. We have this adiabatic. That's when we talk about. Or we say that the heat transfer rate is so small, we can consider negligible. Now, why? Well, we might have insulation. You've had insulated coolers and things of that nature. You know that there's going to be heat transfer. It's going to seep out. If you've ever been someplace where there's insulation over an industrial process, there's been this silver like coat of fabric on the outside of it. You still feel some heat, but we're going to assume it's so small it's negligible to the process. Okay, you might say it has a small outside surface area. That area compared to the surface area compared to what's inside of it, there may not be a lot of heat leaving the system. You might say that your delta T is small. We know the heat transfer rate. We found this from conduction, convection, and radiation. Okay, that's what we found in previous topics here. And what's going on there? What was the driving factor with heat transfer? Delta T. And if that's very small, you're going to have a very low heat transfer. Okay. And then the other thing we could say is we have a very quick passage our flow through our system, and we can see there's no heat transfer. I mean, heat's trying to be given off all the time, but if you look at our system, maybe it's a pipe, and you're traveling really, really fast, the heat doesn't have time to leave the system. It's starting here and it's all the way over here. That control volume which we're following, that mass that we're following, it doesn't have time to leave that system in that area that we're looking at because it's just going through it so quickly. Okay, so that's what we can talk about for Q dot is equal to 0. Now we can also have that our power is equal to 0. Our rate of work is equal to 0. So how are we going to look for that? Well, remember, this is our control volume power. So we're going to say, are there any shafts? If there's no, then W dot CV is equal to 0. If you don't have a shaft going in or out, either adding power to a system or taking power away from a system, you're not going to have any power. Okay. You can say there's no electrical work. Okay. Is there not any circuitry in that we're dealing with? Not. There can't be any power. Okay. Displacements. No. Then we're going to have this power is equal to 0. Now, we're not going to be dealing a lot with piston cylinders. Now, you know that or you may know that a traditional piston cylinder, the one that's in your car, is actually an open system. There is an injector and there's an exhaust. Okay, so there's going to be that, and there's going to be that pistons moving up and down. And we model it as a closed system. It's not really a closed system. The bigger systems we're going to be dealing with now, the control volumes we're dealing with now, are going to be big things like pumps and heat exchangers and turbines. Let me tell you, if you're ever on an industrial visit and you see some of these big equipments and you see it start bulging out like it's going to, expanding, run. It's not. We shouldn't have any displacements in the things we're dealing with here with the open systems. Not a thing. The first thing we're going to have really the most is going to be this. This is where we're going to see most of our work happening, or most of our power happening. And because we're dealing with these big systems, it's quite often that our change in kinetic energy and our change in potential energy, these are going to be equal to 0. These are usually very small. I should say approximately equal to 0. Very small and equal to 0. We're going to be neglecting kinetic and potential energy, but we've been doing that so far already. Potential energy changes are going to happen when we're dealing with pumps. As you're pumping from a low altitude to a higher altitude, that's the only time really we're going to be dealing with potential energy. Kinetic energy is going to be something that could happen in almost any problem. But as we'll see from calculations, that's usually a very small number. It's usually only becomes an issue in nozzles and diffusers, which happens to be our very first control volume that we are going to be dealing with in a few minutes. So what our goal here is going to be taking this first law and going to be manipulating it in such a way that we can analyze it and with the systems that we're dealing with. So we're going to spend some time today talking about nozzles and diffusers, and then we'll talk about on Wednesday we'll talk about some more control volumes, more typical control volumes, and we'll start analyzing them over and over and over again to try to get some practice here. But it all comes back to this equation: the change in energy of our control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in, and I should place summation here to be quite honest, Hn plus Vn squared over 2 plus Gzn minus the summation of my mass flow rates xting times my enthalpy xting plus my kinetic energy xting plus my potential energy xting. I could rewrite this at steady state. If at steady state, I could rewrite this as Q dot CV plus mass flow rate in, so it's a summation, times enthalpy in plus the kinetic energy in, plus potential energy in equals the summation of my power plus the summation of my mass flow rate exiting times my enthalpy exiting, kinetic energy exiting, and potential energy exiting. This is basically showing here energy in, and this is showing here energy out. Okay. The other competing textbook with our textbook here deals with this. They talk about the equation this way: energy in, because heat transfer in is positive, mass flow rate in is positive, and coming out we're going to have work out is positive, energy out here is we made it positive here as we rearrange the equation. This is how they look at the problems. It's an acceptable way to look at them. I like to go back here to this original equation and just deal with it that way, but you can always go with it here. Now, I do want to say one last thing before we end this segment and go on to looking at nozzles and diffusers. If we have one inlet and one exit, what we know is we don't have to really work with a summation. We know that mass flow rate in is equal to mass flow rate out, which we can just call mass flow rate. And so here, if we also deal with that steady state, we can say that 0 is equal to the summation of our heat transfer minus the summation of our power plus the mass flow rate times H in minus H exiting plus V in squared minus V exiting squared all over 2 plus G Z entering minus G Z exiting. Okay, we can write this. So there's a lot of different ways that we can write this. There's a lot of different forms we can write it. And I don't want us to start memorizing these at all. I want us to use them. I want this to be a language that we know how to speak and not just certain words and certain phrases that we have memorized and understand. I want us to be able to converse with it. Last thing, I promise is the last thing. Sometimes when we take our Q dot and we divide it by our mass flow rate, this is going to be Q dot is in kilowatts, and mass flow rate is going to be in kilograms per second, right? And what was a kilowatt? A kilowatt is a kilojoule per second, and a kilogram per second. The kilograms, these cancel, and we get kilojoules per kilogram. Okay, it looks like units we had before, internal energy units, enthalpy units. But no, this is when we're dividing it by mass. The seconds go away because we're dealing with the same rate scale. Sometimes we can call this specific heat transfer. Okay, doesn't that make sense? When we divide it by mass, we divided volume by mass, we had specific volume. Divided by heat capacity by mass, we got specific heat capacity. Here, this is going to be specific heat transfer. And remember what we do when we divide things by mass, and we call them specific volume, specific internal energy, specific heat. We make them a lowercase q. We make it a lowercase letter, so we can do it that way. Same thing happens with power. When we divide it by mass, it has the same units. And I'm doing this. Let me make sure. Let me just do this in this is going to be in BTU per second divided by pound mass per second. We're going to get BTUs per pound mass. And this is specific work. And sometimes that's called a lowercase w. Now we don't use that a lot in this class, in this book, but you're going to be referring to other things, and you'll be dealing with other problems. And this is a language they use in some of the problems. They deal with specific work, lowercase w, and specific heat transfer. Now, I also want to make sure that you don't think that these units can be transferred between these. So the units here, English and SI. I could have flipped the units and presented Q dot in SI or English, W dot in SI or English. It's not that these have to be in, work is in English and heat transfers in SI. I hope that doesn't confuse you. So just make sure that you can do it with both those units, and you'll be good to go. Okay, next thing we're going to do, we're going to go talk about a nozzle and a diffuser.